about the famous black hole. And as you can see in the background, he's not in Taiwan. He's under quarantine on himself. What's it called? Sheltering at this beautiful cabin. You can see that from the Christmas light hanging there. Okay, let's welcome Paul. Paul, you can start. You can share the screen now.
Okay, let me share my screen. So, can you see that one?
Yeah.
Okay. So, you know, it's my pleasure to be giving a talk here. Unfortunately, I'm not on site in Taiwan, so this is a problem for us. But on the other hand, it allows us who are on the internet to swim around and attend many conferences if they're available. So Adam's talk is the third Nobel Prize talk I heard this week. It's just wonderful to see the exciting work. So my job is to tell you about the Nobel Prize work in the Galactic Center. So last year, as you remember, I came to talk about our image of the black hole in M87. So this was the image, right? And as you remember, this is a great result. Can you see this? Google thing. I hope you guys can see this. One of my problems is getting the file to show properly remotely. Can somebody tell me that you can see the second slide? Yes? Can you see it? Are you looking at the first slide or the second slide?
The first one.
Still the first one. You cannot see the, when I change slides, you cannot see it?
Not.
Apparently not, okay. So I think I need to come back to this size scale. Let's see, can you see this? Yes? Can you see my second slide?
No, sure.
We don't see your share screen yet. We only see.
Okay. Hang on. Let me try again to share the screen. So this was my first slide. This is my second slide. Can you see that one?
That's okay.
Now you can, right?
Yes.
Okay. So last year when I came, you know, I showed that, you know, this great result that was very popular about the shadow supermassive black hole in M87. This made it possible for us to measure the size of the mass of M87. So it was a very powerful result. And last year, I also explained why black hole is so important because, you know, it's an invisible phenomena, presumably, and also where gravity is strongest, right? So, you know, we have varieties of black holes, small ones, big ones, supermassive ones. But these experiments that we talk about is always about optics and missing information. So the great achievements in physics is also always about how to tease out the information that's missing as we measure them, okay? So last year I also showed this slide, which is supposed to show that the gravity is in the end, you know, in the most interesting part is when they are, you know, supposed to be the unified force is the super force at the end where all the other forces are combined because of the extreme conditions. And that is, of course, also we are hoping that the black hole environment would allow you to see those extreme environment situations, right? So last year, I explained that black hole research, there are three ways that we can do it, you know, hear it, feel it, and see it. So hearing it was the detection of the gravitational waves. We have tens of cases, right? And then the motion around the event horizon, there's one case, which is the galactic center. And that's what I call feeling the gravity, right? And then, ourselves, we are working on imaging at the event horizon. And all of these things are studying the GR effects. And the interesting thing is the common techniques always using lasers and interferometers. So are these Nobel Prize winning work? This is always what I was asked last year. And last year, of course, when I came by, gravitational waves was the Nobel Prize winning. But as you can see, not only hearing it gets the Nobel Prize, feeling it has now also get the Nobel Prize in this experiment. So what I want to do today is to go back and give you the background, a little bit more detail on how these things became Nobel Prize winning works. There's a common thread in how these things became so important, right? So as you know, the LIGO is just an interferometer experiment. It works on two arms typically, where the laser is bounced between mirrors, and then we measure the separation of the mirrors very carefully and listen for this ripple in the stability of this separation of these two arms. And of course, by having several sites, you can have the simultaneous detection, and then the separation in arrival time of that signal at the three sites allows us to say roughly which direction it's coming from, right? So there's a very clever idea of using interferometers in this mode in order to detect. And the signature, as you might remember, it's a very short signature on the order of a fraction of a second of time. This is running along in the time axis below for three arms of the LIGO interferometer. This one is the signal to noise of the signal of the ripple. This is actually a frequency response as a function of frequency. When the signal comes through, you can see it starts out at a somewhat lower frequency, and it comes to the real signal, it comes a higher frequency. And this is actually the stress or the distortion that you can see, lower frequency rumbling, and then somewhat higher frequency, and then it dies off, right? So this very classic signature of this ringing, which is why we call it hearing, because the sound is, this rippling frequency is on the order of 50 hertz or so, so that's the realm of what we listen to, right? Of 50 hertz. Now, then we see that, this is just a sample that, we always see this classic signature. We have many examples of these things now, of this ringing pattern. And this ringing pattern, we now recognize to be probably a colliding neutron star or neutron star with a small black hole. The research now, is heading in the direction of looking for gravitational wave and precursors. These are very fancy experiments now to try to find the gravitational wave, and you can appreciate the problem. The signal only comes for duration of a fraction of a second. And from there, you have to go find where did it come from, what was it, and what kind of phenomena it was. So it's quite a detective story, and there are more telescopes coming which will explore more sensitivity. Whereas the more sensitivity being useful is that you might be able to extend for the in spiral phase, as the two things combine, you can pick up the earlier phase before it hits, maybe on the order of minutes, and then actually post-merger to extend the detectability of that stage a little bit further. And of course, many more detections when you have more sensitive systems. We are all very excited if you can actually see supermassive black holes mergers. Of course, these will be much more interesting phenomena because these are not going to happen very slow, very quickly on the order of fraction of seconds. It may be detectable on over longer time scales. So these are experiments that we are looking for to come. Now, a little background on why this thing is interesting. At the beginning, before you guys all showed up, Adam and I were discussing how he and I overlapped at Harvard. When he was at Harvard as a graduate student, I was just beginning to teach as junior faculty there, right? So you never know when you're teaching which one of your students is a Nobel Prize winner on the stage, right? So, you can see that the possibilities are there. We need to pay attention, right? You can say, I wish I had him for a student in those days. But here are the other detections, okay? Nobel Prize were given by Nobel for gravitational waves actually twice. The first one actually went to Taylor and Hulse. Joe Taylor detected the binary pulsar spin down And this experiment was done on very famously on the Arecibo Observatory, which you all know have collapsed in the last week, right? That very large telescope was the site where they detected the pulsar spin down signal. And I remember very clearly, I was a postdoc at UMass. He came back from the experiment in 1978 from Arecibo, and he showed the measurement of these pulsar signature, where they are measuring the pulsar arrival time and detected a tiny, tiny slowdown of the period, which was consistent with the calculation for gravitational wave being emitted. It was such an impressive talk, you know, just a lunch seminar coming back from the telescope. I immediately thought, this must be Nobel Prize winning work. And within a year, Princeton recruited him, right? Before he got his Nobel Prize in '93, the experiment was done in 1978. And then Ray Wise and Kip Thorne and Barry Barish obtained this experiment for gravitational wave detection in 2017. Ray Wise was actually working on detectors in the 1970s. Here he is as a young professor working on these detectors that will eventually would be for the CMB experiment, which also had a Nobel Prize. And people said, you know, well, should he have gotten the Nobel Prize for CMB? Well, they didn't give it to him for that. But, you know, good people don't just sit on and feel sorry for themselves. They just go out and get another one, right? So that's what he did. So the backstory on this actually begins with Einstein's paper on quantum theory of radiation in the 1917, okay? Following which Charlie Townes had discovered the maser phenomenon. The maser phenomenon is basically amplification of radiation between two levels in an atom where, or molecule, where the radiation is locked in by the quantum theory, and you can overpopulate the upper state and stimulate radiation coming down from the upper state to the lower state. Well, Townes was able to construct this maser, which eventually, when you study the species that works in light, it became the laser, okay? So Charlie Townes in Columbia had discovered this maser and then laser, and by 1964, he and a couple other people were not Nobel Prize for maser work and quantum electronics. And then he moved to MIT in the 60s, okay? He was at MIT at that time. I arrived at MIT in 1968. So again, you know, I just want to tell you the backstory, how I actually saw this happening. You know, in 68, I was in a freshman. You know, I went to the evening donut seminar. I went because there were donuts, free donuts as a freshman. That was the great attraction. So for the students listening in on this, when you go to eat donuts, you have to pay attention to what's actually happening to the other people who are not eating donuts. Well, they were discussing what is the most important experiment in physics at that time, and they want to make use of lasers, which was coming online in the laboratory at that point. I myself was trying to make a liquid dye laser work because the liquid dye has a variable frequency that you can tune the laser. So this was thought to be very interesting. Ray Wise at that point was an assistant professor. He was working on the CMB and also lasers. Well, 50 years later, they have accomplished this tremendous experiment for doing gravitational waves. So I want to point out that this experiment begins with the phenomena of lasers being utilized in the laboratory, right? So when you have a very good technique, you use it in the laboratory, sometimes you can make tremendous discovery. Well, what happened to me was that at freshman, I started to work on this. After 3 years, I gave up laboratory physics. I thought it was too difficult. I decided to do astronomy instead. So you have to be careful what you choose in life. Okay, next, gravity can be felt. So here's a picture of the gravity experiment of the Max Planck group. This is Reinhard Genzel's results. And you can see this picture, a movie of what happens. This is a star field. You can see 10 light days zooming into the center of the galaxy. And you can see these stars moving in the field, one of which is whipping around in an elliptical orbit. The orbit, this is just a looping in the movie, okay? You can see this star looping around in an orbit precisely elliptical on a scale of 15 years, okay? This is the Nobel Prize winning work, okay? It was this measurement, detection of this elliptical motion of this star around the center where supermassive black hole is right here, where the cross is. Going around this in classical orbital mechanics, right? One object moving another under traction of gravity, you define the orbit, then you can measure the mass content at that central part, okay? The discussion there wind up to be the Nobel Prize work in this year, given to Roger Penrose for theory in Oxford, Reinhard Genzel, Max Planck, and Andrea Getz at UCLA. And here's a picture of Andrea younger, in her younger days. She's actually a lot younger than us. She's now in her 50s. And there's Reinhard in 1980s. He was at that time postdoc working with Charlie Towns. So there's the Towns connection again, the lasers, okay? Why was this stimulating this particular important experiment, right? So there's the story. So the galactic center, here's a picture in the radio. On the left, this is a low frequency, 90 centimeter. And as you go to shorter and shorter wavelengths, to, I think this is 6 centimeter, this is 1 centimeter, you zoom into the middle part of this galaxy, and you can see that in the radio, there are lots of interesting things going on in the center of the galaxy. All of these tiny little bubbles are actually supernovas, the kind of things that atoms would be measuring on a very large scale in the universe. But inside the galaxy, of course, there are many supernovae going on, and including in the middle, we think this is also a supernova, okay? Right in the center of the galaxy. And within the center of the galaxy, there's this spiral-like pattern, okay? All of this stuff is now resolved. They're out here somewhere. And in the middle, there's this spiral. And if you zoom in on this, you see a little spot, unresolved little spot. That's what we call Sagittarius star, which we thought might be a black hole. Why? Because we couldn't explain its radiation in any way. But that doesn't tell you that it's a black hole, right? You actually have to prove that it's a black hole. How do you prove that it's a black hole? You have to demand that there's a huge amount of mass packed into a small region that satisfies the m/d relation that allows you to determine that the object has so much mass that light cannot escape, right? So this m/d measurement is the crux of this Nobel Prize. How do we know the properties of this particular point source? In the radio, we could not do it, okay? At that point. Now, what is involved in doing this? What involved is always about introducing a new technique. So in this case, astronomers need what we call adaptive optics. Okay, what is adaptive optics? Explain this, okay? So when you take on a telescope, you take a picture of a star. If you have a very short exposure, this is from Lick Observatory on a 1 meter telescope, a very short exposure, you'll find that you don't get a point source when you look at a star. You get a bunch of bouncing around things, what we call speckles. Okay, so these are the diffraction scattering due to the atmosphere. The atmosphere between you and the star is so terrible that in any moment, the image is just bouncing around, okay? So if you integrated that for a long time, you just get a very blurry thing. Of course, this is what we call seeing, right? The seeing conditions, depending on the site that you put the telescope, sometimes good, sometimes bad. It just means that the sky conditions are good or not, so that the this kind of scattering effect is important or not. So for a long time, what is the most clever method to do is a very, what we call a blunt instrument approach. You just take very short exposures of this, and then you stack them. And if you're short enough, usually the point is, most of the flux is still in the middle. You center on them, and then these random speckles will get beaten down, and then you recover over an integration a sharper image than what you would get if you didn't do this. So very short exposure, stacked together, this is what you get. And then came in the 80s, the adaptive optics. Now, adaptive optics is tremendously important because it actually tried to compensate for the sky conditions, okay? How the sky is affecting you in the measurement. So this next slide shows the technique of adaptive optics. Interestingly enough, This technique was developed by the military. You might think, why would the military be interested in this? Well, this is in the 80s. I was by that time, I was out also at Berkeley at the same time with Reinhardt. We were Miller Fellows at Berkeley. And at that point, some of this technique was starting to filter out from the military. They use this technique, of course, you might think about it, they would like to see sharp images on the sky, right? Why? Incoming missiles, you would like to be able to see them. So they developed these techniques, and eventually after a while, they declassified them and pass it to the astronomers to use. And in Berkeley, we have an interface at Livermore Laboratory where we have fans in to do classified military work, fans outside the fence where we did a lot of astronomy work. And we work together. And this technique goes sort of like this, incoming light, we pick off the light, and then with a wavefront sensor, measure the distortion of the atmosphere. And from there, we feed back to another mirror, which has a rubber-like surface, which we immediately try to simulate the distortion coming in from the sky. And that straightens out the wavefront and then produce a more corrected image, okay? So on the right here, what you see is from the UCLA group. With the adaptive optics off, it's a blurry image. With the adaptive optics on, it becomes a much sharper image, okay? A very blurry image becomes a very sharp image. What does that do? That allows you to see very faint things like the S2 object, which was the object that was going around the galactic center in the middle over time. If you didn't have this technique, it would be very difficult to pick the motion out of this soup as to what's going on underneath, okay? So this is the technology that was involved using adaptive optics. And they did this with a wavefront, and the more clever manifestation of this technique is to shine a laser up into the atmosphere, into the so-called sodium layer, where you can make the sodium laze. It becomes a spot, very bright, because we stimulate that transition. Okay, so this is the application of laser twice. On the ground, we shoot a laser up, and in the sky, the laser phenomenon happens and creates an artificial star from which we do this adaptive optics. So with this method, this 26 years of observation of S2 is shown here. So this measurement is 2 orbits of the S2 star in orbit around the galactic center. You see this elliptical orbit. It takes 15.5 years to get around. On the first time going around, they define the object in the middle and measure the mass. That is the Nobel Prize winning work, okay? It was the ability to measure these points very, very accurately, not only once, but now twice. And what is on the right here, first is to see that over short period of times as it swings around the galactic center, we measure the positions very accurately. And in addition, because it's a star that we're measuring, it has an atmosphere that we can measure its lines and we can measure its motion. The velocity of gas tells us the third dimension, the radial dimension of the motion. And you can measure this and you find this motion that tracks this rotation, okay? The elliptical orbit not only goes measure this motion, we also see the radial motion, which is consistent. And that gives us the 3-dimensional structure of the orbit and therefore the mass in the middle. Now, that is already quite beautiful, and that is the Nobel Prize winning work. But these people do not stop. Of course, they continue to try to measure this very accurately. And in 2018, on the second swing through in April and May, you can see that it's moving very quickly on the order of days. They can clearly see this motion moving at 8,000 kilometers per second. And you can see the size scale here. This is 10 milliarc seconds, 15 milliarc second is a very fine motion around the center that they're able to measure. And how are they able to measure this so accurately? This is from the group in Germany, Reinhard Genzel's group, and they use interferometer. 8-meter telescopes, 4 of them together, operating as an interferometer. They pick off in the sky one, which is the AO Guy star. This is the star that they used in order to do the adaptive optics to sort out the sky condition. in order to flatten the sky in terms of atmosphere. And then within here, they actually pick another star, which is used to track the fringe of the interferometer that they have built using those 4 telescopes. So 1 star to apply the adaptive optics, 1 star to track the fringe of the interferometer to measure the baselines, because the baselines on the sky is rotating all the time, and then high angular resolution when they reassemble, and then the baseline produces a resolution on the order of 3 × 10⁻³ arc seconds. This is tremendously good resolution with a astrometric relative positioning ability at 40 micro arc seconds, okay? And this is very important, and I show you the diagram of this, which is the benchtop idea of how to do such an experiment. This is just like a laboratory optics experiment. You have light coming in, split off, wavefront sensor, in order to adaptive optics correction, and then pass it through this system. This is called delay line, which has to compensate for the fact that the mirrors projected on the sky, those 4 telescopes, is changing as the Earth rotates. So this projected separation between the telescope is changing, and we have to compensate for this delay. And then later on, a lot of optics to combine. And finally, about a few % actually hits the detector in the end, and they measure this result, okay? So it's a very fine results. And with the nice now ability to show that as it goes through the closest approach, this is post-Newtonian calculation incorporating general relativity effect, they see the additional motion. So this bottom line is just a straight classical orbital motion in this elliptical orbit, what you expect the motion to be. And then when it gets close, this is the extra boost in velocity on the order of 200 kilometers a second due to the GR effect of the central object being so massive. And this effect has been measured both by the UCLA group and the Max Planck group now. And the very interesting results in here is that also the orbital motions in the terms of the innermost stable circular object, they see a hot spot in the Sag A star, and that hot spot is moving around in this pattern, which they can determine to be in a circular orbit, roughly circular orbit. This is with time. You can see the motion, and the size scale measures, and it measures to be about 3/10 the speed of light. This is from the Gravity, which is the group that built this special interferometer for the very large interferometer experiment in Chile. So this 0.3 light speed of light is very close to the event horizon. That's why it's so high in speed, and it defines this particular motion, okay? So beyond that, of course, is actually more important is that you can actually calculate the orbit now by demanding it to be a general relativity orbit, meaning define this orbit very accurately, including all the GR effects, and then you calculate this deviation of the orbit relative to this GR predicted orbit. And you can see that it follows the orbit extremely well with the residuals extremely small. And this says that this ellipse from one orbit to the next actually has a precession of a predicted precession of about 12 minutes of arc as it completes, okay? So it's not the normal classical elliptical orbit, but slightly tilting this way, prograde by about 12 arc minutes, okay? So I'm saying that this very fine experiments, which measures not only the positional deviation, but also the motion in velocity. Here's calculation again, expected GR orbital fits in terms of the RA direction in one direction and the deck direction. And this is the measurement with this gravity interferometer instrument that they have built. And you can see that follows the predicted GR deviation very accurately. The flat line is the stable circular orbit, and the prediction of the GR effect is here, okay? So this is the change in velocity that's predicted, change in angle is predicted in separate direction in RA in deck, and you can see that it follows this deviation very well. So you can say, why is this so good? And that's because increase in precision. Okay, so here's a measurement of the position uncertainty with time. When they started this experiment, the precision was roughly here. And by the time they got to this orbit again, closest approach, you can see 2 orders of magnitude improvement in precision. So this is the basic message in Nobel Prize winning work. You know, you have to get the precision down really well in order to get to Nobel Prize winning work. Now, this is because of the interferometry, and this is because the instrument has gotten so good. So future research, you know, again, will involve larger telescopes, which will give us much more accurate measurements, more sensitive detections of fainter targets potentially within the orbit, and also allow us to look at the gas infall. So gas infall is actually quite important because they actually right now can see in the near infrared, this is 2 micron, 4 micron, over 4 years, they can see an object which is moving. Okay, the interesting thing why this is so important at 4 micron is that we think that this is a gas phenomenon. And this gas phenomenon is coming in like this, in an elliptical orbit also around the supermassive black hole. Why is a gas object important? Because of course it is not held gravitationally bound like a star. So therefore the tidal disruption effects is more likely to happen. And we expect that this might lead to a feeding phenomena for the galactic center. So the data shows that this blob here, this is a plot of velocity they measure versus the position relative to the galactic center, and with time from 2004 running to 2018 in 2 rows, and you can see some object moving in over time, getting closer and closer to the center, swings around and appears on the other side. Okay, so this is the orbit predicted, and this is the gas coming. The interesting thing is not a isolated phenomena. There's yet another body behind it coming, which will get close. So with sensitivity, it's likely that we might be able to see infall into the galactic center. Okay, so what is the backstory on this stuff, and why is it important about feeling gravity for this Nobel Prize winning work? Again, Towns is involved, okay? So in the 60s, when I just arrived at MIT as a freshman, Towns had left. He had gone to UC Berkeley in 1967. From there, he established an infrared group, and he also started to begin to use the infrared to measure the galactic center motion. And around 80 was when Reinhard Genzel joined the Towns group, and he begins to study this phenomena of the galactic center using various lines. Okay, the original idea is that if you get close to the center, the gas motion will of course be increased because of the larger potential well that you're living in, right? So just from the line width itself, you will know that you're near the galactic center. So the idea was to use the increased line width to locate the mass and use the line width to determine the gravitating mass. Okay, so he joins the group and starts to work on this. And at this point, Reinhard moved from VLBI to infrared astronomy. His PhD work was on VLBI. So while he moved to infrared astronomy, I moved to submillimeter interferometry, and we were both at Berkeley. And then he began to measure the orbit of S2 in 1992. 15 years later, the orbit is defined. This is Nobel Prize winning work. 15 years later, even better instrument has been built to now really measure very interesting stuff. So 50 years later, again, a 50 years experiment, Genzel and Getz wins the Nobel Prize for feeling gravity. Well, unfortunately, at that point, I started to work on imaging black hole, right? So it's another choice of direction of what you should do. So Nobel Prize winning work is defined by precision. The science is always addressing very fundamental physics. The precision is the very important part, and the science typically has to discover, of course, address very important phenomena. This is the key. And then, you know, new technology is important. Why some Nobel Prize winning work are stimulated and why it's not. These are the important questions that we can always contemplate. So finally, let me update you in the next 5 minutes of what happened in the third part of the thing, which is seeing the black hole, right? So last year, I told you about the M87 black hole, a very large mass confined within about 100 AU, the solar orbit type size. is very far. Of course, that's what makes it so difficult. The Schwarzschild radius is 10 micro arc second, okay? And the black hole size is 5 times 10 to the minus 9 size of the moon. So the point here is that the precision is extremely important. We have to get down to a precision of 20 micro arc second. Remember, the gravity experiment had a precision of about a few milli arc second. So our absolute precision has to be much better in order to do this experiment because the object is far enough away. Okay, so very long baseline interferometer. It simulates a very large telescope, but there's lots of information is missing because we are only sampling a few telescopes and we are synchronizing the wavefront. So this is again the adaptive optics problem. Okay, the wavefront is coming over your collection of telescope. You need to be able to correct for that wavefront to a precision of 40 micron, the surfaces, over intercontinental distances of 10 kilometers, 10,000 kilometers. So that is the physical difficulty of the experiment, okay? To do the adaptive optics, to measure the front, wavefront, to that kind of accuracy, correcting for many effects, atmosphere, electronics, telescope, etc. Of course, this particular technique already won the Nobel Prize from Ryle and Hewish in 1974. So you all know this is just distorting the space, right? Distorting the geometry, and this leads to the bending of the light around this, right? And the image is produced because the light, which normally would have gone towards you, looking from here towards the black hole, that light is bent into the black hole and it's lost, and you get the shadow where the light is lost with a measure scale of 5 times the size of the Schwarzschild radius. And then, you know, this is exactly how interferometer works. The Earth spins, the telescope begins to be measured relative to each other. They build up the sample spot on the telescope, this virtual telescope size of the Earth. And as the sampling increases, the image gets better. So this is a visibility question, which is actually the sampling function, looking at the source plus the error of the experiments, right? And the adaptive parts, adaptive optics part, comes in using one of the telescope relative to the other telescope. We have this thing called closure, which is to measure the phase of one telescope with another and another. And this allows us to calibrate out all the errors. And you can see the original response before the phasing and after the phasing shows you that the error pattern can be suppressed and the flux can be brought up in the middle. So this is very identical to adaptive optics that's used in the optical, except this is much more mathematical and theoretical in the sense that we know exactly how to calculate this sampling function, which allows us to correct for it. So finally, the image looks like this. As you remember from last time, looks like a donut, looks like a hole. It's black in the middle, size scale about the solar orbit, and it has spin that we can measure because the spin is enforced close to the black hole. It doesn't matter what the outer parts of the environment looks like, but in a very close environment, you are forced by the spin of the black hole. And because of this, we can tell that the spin is pointing away from us because the lower part of the spin enhances the radiation so that it's brighter on one side. You know, had the spin be toward us, the bright part would have been on top. Okay, so that the separated bright and dark part of this black hole is very important, and that will allow us to see what the spin of this thing is. Okay, so again, you know, from previous years, the experiment here was to tell you that, you know, as the calculation will show, it depends on the orientation that we look at. These very delicate calculation will show you that the brightness of the ring, the innermost parts, changes depending on the orientation that we're looking at, okay, versus this face-on image. And at the end, the problem is simply that our resolution is not good, so that any type of model, when you convolve to the resolution that we have, it's roughly agrees with the experiment. So this is the main problem that we're facing. And the future looks like this. In 2017, where we did the measurement, this was the measurement. We have 9 pixels across this donut. We are now working on with the Greenland telescope, which will give us 25 pixel across. And we're working on moving the telescope to the summit in Greenland at 660 gigahertz, which will give us 225 pixels across this image. And now this object that's shown here is in M31. And that says even M31, we will have enough resolution to see this donut, okay? So the question, of course, you're asking me at this point is, what does the Sag-A star look like? Because I was supposed to show you this year what the Sag-A star look like compared to M87. And this is the relevance to the Nobel Prize winning work, right? Well, I cannot show you. I'm still not allowed to show you. I can tell you that it's very exciting, but I cannot tell you what it is. Well, I'll tell you that it's very encouraging. So what is the next step? The next step, we think that, you know, we can build an interferometer covering Asia. We intend to build a big telescope, and we can use Greenland, Hawaii, and this will extend our coverage around the globe. The other side is already filled in by the Event Horizon Telescope. We think the next step is to build a telescope on the east side, on the other side of the globe, so that we can have continuous coverage over time. So let me summarize. You know, Nobel Prize winning work, as I already said, you know, involves these precisions and so on. And that the next step, even after this extension to the other side of the globe, we are thinking about moon-based telescope. The moon is about 30 times the diameter of the Earth, and therefore will give us a 30 times to 100 times better linear resolution when we can establish a telescope on the moon, backside of the moon. And this will be an interesting future for this kind of work. So all of these work depends on resolution. The gravitational wave is looking at this coalescence process. The new Nobel Prize winning work is talking about the dynamics around the event horizon, and we can see that tests that I show you about the GR effects. And the upcoming submillimeter VLBI seeing the black hole, we are also probing the GR effects at the horizon, and the higher resolution that we are looking for will allow us to probe the various models of how the accretion process will go and how the radiation will flow in by providing the resolution across that donut. So all of these things are depends on getting more sensitivity and more resolution in all of these domains, in time domain, energy domain, dynamics domain. And there is a future for us in Asia to lead in this particular frontier. So I'll stop there. I think I've used up 40 minutes.
Thank you, Paul, for the very exciting talk. And we now open for questions. Q&A first. So it is possible to take an image of the black hole in the Milky Way center?
Yes, so we have the data. And as I said, you know, I would like to show it to you, but I can't because we're forbidden to show the results until they are ready. But I can explain why I cannot show you, okay? The reason is that, you know, the galactic center black hole is a lot closer than the M87 black hole, which means that it's actually physically a smaller object, even though it's roughly the same angular size scale. The smaller physical size scale means that it's rotating. So as we are doing the experiment, taking data, actually the object is rotating. So to make an image that's rotating is very complicated. You actually have to make a movie in order to do it, okay? So to actually make the movie to fit with the data is very complicated, and people have been working very hard. And this week we had this Event Horizon collaboration meeting, and we're discussing the paper readiness. And we think that it's a few weeks away, a few months away from getting the paper actually out. So we are settling down in the various methods of fitting the data seems to be more or less in agreement. We are still sorting out the differences as to what we agree to or not agree to. And I think when you see it, you'll be pleased that, you know, the interpretation M87 is not wrong. It's substantiated by what we see in the galactic center, and the galactic center image will show new results, which will be interesting in illuminating the physics, I think.
So we should expect it by the end of the summer.
So next year at this time, I can tell you what the story will be.
Okay. Thank you. Yeah, any questions from the local audience? Yes, there's one from the
Summary slide. Basically, you can put the telescope at one.
The last, you want to show the last slide?
So just wondering, is there any some kind of rough timeline for this wide quantity given? With a very long baseline, you put the telescope on the moon.
You mean this slide
In the very
or this slide?
conclusion slide, the summary slide, you mentioned that you can, I think you mentioned that you can put the telescope on the moon. Then
Yeah. Okay. The telescope on the moon. Yes. Well, getting the telescope on the moon is the big problem, right? So once you get there, of course, you can calculate whether you can do the experiment or not. Okay. So the question, of course, will be a signal to noise. The question is, how much resolution will you have to be able to see what you have? Is there enough flux to do the experiment? That will be the key, right? So if you look at the theoretical calculation, you see that actually the ring is extremely thin compared to the donut that we see. That means that the flux is packed into these very small, narrow region. So my suspicion is that when we get up to higher resolution, there will still be enough sensitivity in there because the flux is pressed into a very small region. Okay, if it were truly smooth and you put in a lot of resolution elements on it, then there won't be enough signal to noise. Okay, so I expect that the signal to noise will be there, but this, we need to simulate and then actually articulate what we will need in order to actually do it. So the experiment itself is constantly increasing in sensitivity. One of the limitations is the instantaneous bandwidth that we can process, electromagnetically. So we can process 4 gigahertz. We expect to be able to process 100 gigahertz and more with time. So this is dependent on digital development and recording technology. So people are hard at work to constantly think of ways to collect more light in order to provide more sensitivity even on the same phenomena.
Any more questions? Oh, yes.
You mentioned about local price many times. Yeah, panels imagine a black hole get a local price, and then fail it, and see it, and what's the next? It seems no, I cannot create any work to get a local price in this field. So what must we do if we don't get a local price?
Well, we mentioned Nobel Prize, of course, because Nobel Prize was given this year, right? But as you know that, in physics and other fields, we should not be aiming for Nobel Prize when we're doing our research. It's not the right way to approach things, to aim for Nobel Prizes. But what is interesting is, of course, think about what is important science. That is not an empty question, right? Nobel Prize or not, there are some questions that are more important than others. And we usually call that fundamental, right? Fundamental physics, things that are truly fundamental in nature are more important than other questions. And then you have to ask, how do I make breakthroughs? Not about winning prize. How do you make breakthroughs? Usually, I believe the question, in physics, as well as other fields, the answer is in precision. We need to be able to measure whatever signal that we're doing to get more information. So to get more information, it's about separating the information into more and more bins so that we can understand the details, right? That after all is what interferometry is about. That is what spectroscopy is about, right? You know, that's what energy spectrum is about. That's what transitions are about. It's all about teasing out the photons into the right bins so that we can classify them and understand them and then actually be able to do things. So today's talk, I meant to point to the early days of each of those experiments as to what was the key that drove people. The key was actually the quest for more precision and try to focus the precision on fundamental problems. I cannot tell you which problem will get the Nobel Prize, but I could certainly tell you which ones are technically feasible to increase our resolution. I'm not sure whether I've answered your question properly.
Yeah, just like example, when we calculate second group of the now, I mean the electron device.
So, in the imaging of these black holes, are there any parameters that one can keep track of to potentially indicate deviations from general relativity?
Yeah, so just looking at this picture there are quite a number of models that using general relativity, various aspects of general relativity that predicts the actual motion in here. And then of course, there's very fancy treatment of the dynamics, magnetohydrodynamics that's involved. So usually we call it the GRMHD model. So that tests various aspects of these models. And there are hundreds of these models that have been proposed and that we would like to be able to measure. And the details of exactly how far this piece of the ring and the inner part of it and the outer part of it, how much light is in the inside and outside, has a lot of dynamics that we need to understand as to what actually happens. Because the black hole, after all, is in the middle, right? This is roughly 5 times. The black hole is actually in the middle by a factor of 5. So we need to get closer if possible, but how can you, right? Because most of this light is sucked in because of the shadow, but there are overlying effects, right? Things along the line of sight in the third dimension that allow us to probe even more, right? So we don't understand the physics and completely understand the GR effects at this point. And of course, as you know, the GR correction, there are many orders of corrections that we have to check, just like the gravitational wave detection. That ringing, the exact ringing profile carries slightly different signatures depending on the correction terms that we take in the GR model, right? So people are working on all these things to test the higher and higher order effects. So this particular experiment that we talk about only checked the very low level effect, right? I mean, almost 0 order effect of GR, the fact that you actually get the shadow, that's the prediction. But exactly how things look will be revealed, I think, with more data of higher quality.
Thanks.
So in how many years you expect that the data can give us some feeling that we can do some precision GR?
Well, I think the typical yardstick is 30 years in any of these problems that you can imagine. We are accelerating in terms of the techniques that we are able to bring to bear on physics problem, biology, chemistry. All the techniques are improving very quickly. But I remember that, when I finished my PhD, people asked me, can we do research on black hole? And I just said, no, cannot be done because, you're talking about size scales that's way too small and signal way too little, to be able to do work. But, no sooner have I said this, I realized that things are changing. In 1980s, when I started at Harvard, okay, X-ray was just starting in astronomy, X-ray. And the analysis talked about whether we are detecting 3 photons or 2 photons in astronomy, in X-ray. That's how rough the field was, right? Today we're imaging, making pictures, you know, like real pictures, you know, already for many years now. So that has to come about because of technical development. And the stuff that I myself am working on, it's not possible 30 years ago, but the technology has greatly improved, right? So I think 30 years is a good yardstick for thinking about what can be done.
So it's about the right time for the graduate student to know.
Oh yes, oh yes. So you know, you look at all those Nobel Prize winning work, again, sorry to have to say that, but you look at when they do it, you know, it's actually when they were all quite young, you know, 30s, typically. How old are you? It's too late.
Wow. Yeah, I started working on physics 30 years ago when I was a graduate student. So now precision things goes on.
So young people at the 30s and 40s, you know, these are really the golden years. You know, Adam Rees's work for Nobel Prize winning work was done immediately after his PhD.
Any more questions from the audience who are excited about the future of Nobel Prize? Okay, I do not see any more. We thank you, Paul, for this exciting talk. I wish you a good evening in your
Very happy to be there. I hope next year to be in there in person.
Yes, we expect to see our Milky Way black hole.
Yes.
Okay, thank you.
Okay, take care.
And is the next speaker? So let's come to the. Oh, next speaker is already. We can already see his image. Professor Chen. Okay. He will talk about another exciting topic about gravitational wave science, from black hole physics to macroscopic quantum mechanics. Professor Chen, can you share the screen or the mobile?
Yes. Can you hear me?
Yeah, we can hear your voice. Make sure everything works.
Okay. Let me see whether I can share my screen. Does this work? Is this working?
About the next page, I mean, you press the next page to see if it works simultaneously.
Oh, does it work? Oh no, it's not working. Let me share another. Sorry. I'll share the full screen. I think the full screen. Oh, okay, this way. Okay.
Can you press the next page to make sure the next page works? Oh yeah, okay, you work well. All right. So let's welcome Professor Tsing. Okay, he's from the California Institute of Technology, and today he will talk about another exciting topic about the black hole. Let's welcome Professor Tsing.
Thank you very much. It's a great pleasure to come to the NCTS. I hope I could have been there in person. So today the topic of my talk is about gravitational waves. Let me start just by just a brief introduction. Gravitational waves are perturbations on the space-time curvature. So here, for example, you can see you have a background space-time curvature, which is like the surface of this orange, and then you have the little ripples here, which corresponds to smaller scale perturbations, which corresponds to gravitational waves. So these waves can be emitted by oscillating matter, and they propagate at the speed of light according to relativity. And then the leading order emission is quadruple radiation. And then the gravitational wave causes changes in relative positions of free test masses, and the amplitude of the wave basically corresponds to the strain it induces in between objects. So there's a long history of gravitational wave detection, just like Professor Hall was talking about. Every field, it takes a long time to develop. But I think right now is also a very good time to enter gravitational wave research. So basically, the detection started in the 60s with Joe Weber, and he was using resonant mass detectors. Later on, Ray Wise and others proposed to use microsync interferometers to detect gravitational waves, and they soon realized that you need 4-kilometer sized microsync interferometers to actually reach sensitivities that will be meaningful for detecting astrophysical, gravitational waves. So, in this picture, I'm showing the LIGO detectors, and then these are 4-kilometer interferometers that started operating 20 years ago in 2000. And then actually the first science run for the LIGO detectors was when I was a graduate student, around 2003, I think. But it was the second generation of detectors that actually made the first detection in 2015. But then in the past 5 or so years, we have detected around 100 pairs of merging black holes, one neutron star binary merger that also induced electromagnetic counterparts. There were a few more detections which involved neutron stars, but no electromagnetic counterpart was detected. So the detection in principle is very simple. It's a microsync interferometer where light comes in, measures the differential arm length change induced by the gravitational waves. And then it's the very good sensitivity here, which really these detectors are able to right now measure a strain of 10 to the minus 23. Okay, so this is really the sensitivity that enabled the detection of gravitational waves. So in my talk today, I will mainly talk about using gravitational waves to study black holes, like a little bit related to the previous talk, and how you would demonstrate and test predictions of general relativity in the context of black holes. And also, looking more toward the future, what kind of physics you might, or exotic physics you might look for, and using gravitational waves for studying the evolution of the universe and large scale structures. Towards the end of the talk, I would also talk, a little bit about, what the fact that we have such a good sensitivity on measuring positions of test masses. These are in the regime of quantum metrology. It turns out that we can use LIGO technology to study the quantum mechanical behaviors of macroscopic objects. Even in some cases, maybe speculative, but looking for the validity of quantum mechanics, whether there are violations or whether there are new effects when quantum mechanics and gravity are involved in this regime. So let me first briefly introduce one of the major kind of waves that we look for in LIGO. These are the mergers of black holes. At the beginning, these two black holes, they circle around each other, but then due to the radiation of gravitational waves, they lose energy, and then their orbit gets closer and closer, and then the amplitude of the wave would increase, and then the frequency of the wave would increase up till the moment when the two black holes will touch, and then they go through the merger stage, where they merge into a final black hole, and the final black hole will ring and then give you a so-called ring down wave. I will go into more details later in the talk. Here, the more the point is the time scale. So basically this illustrates the first detection. The two black holes are around 30 solar masses. And then the frequency at which they emit these waves are like around 200 some hertz, up to 200 hertz. And then the lowest frequency that we were able to catch these waves here are around 40 or 50 hertz. So this is in this acoustic frequency band that we're detecting these stellar mass black hole binaries. So this is the first event that we detected. And the first binary neutron star event was also very exciting. It turned out to be, it triggered a lot of astronomical interests. In 2017, and then there was this event, 170817, so-called, and that was a merger of binary neutron stars, which triggered gamma ray burst, and also a lot of other emissions in the visible and other frequency bands. So this first detection of neutron star binaries also was observed in the, somehow I can't point. That's okay. Sorry. Maybe I should do this. This way I can point, I think. Let me zoom in. So basically, so this was also observed, in the different frequency bands of the electromagnetic spectrum, and this triggered a lot of interest, which revealed a lot about, what happens after the neutron stars merge. There are matter that are ejected, and then these matter then will go through nuclear reactions that produce heavy elements. Okay, so it's a very interesting process for observational astrophysics. So after the first detection, there was a few science observation runs of LIGO, since then, in the so-called 01 and 02 runs, which were like, the dates are shown here. Basically, I think it was more like a year of observation. We detected 10 binary black holes in total. And then the more recent release of data and the release of results was from the first part of the so-called 03 run. So the 03 is the third observation run, which was from the April of 2019 to the April of 2020. So in this event, and then in the first half of the 03 run, the data was released, and also there were 39 events that were released from this catalog. And among these, as you can see here, most of the events are binary black holes. Some of them are possibly binary neutron stars, and some of them are possibly neutron star black hole binaries. It actually requires a lot more sensitivity for us to really say whether these are, either binary neutron stars, binary black holes, or neutron star black hole binaries. So you can refer to these two papers for details. So from this, the immediate information you get are the distributions of masses of these individual black holes. Shown in these columns here are the mass of the primary black hole, which is the heavier one, and also the mass ratio. And also the chi effective here describes the effective spin parameter that measures, how fast these are spinning. So predominantly the conclusion seems to be that these black holes are heavier than what we had thought before. I think maybe the more of them are 30, 40, even, there were like, even one pair of binary was more approaching, the total mass is more like 150 solar masses. These are really heavier than what astrophysicists were predicting before. And also it turns out the spins of the individual black holes, most of them are pretty low, which was also a little bit surprising. But later on, Jim Fuller et al, they explained the low spin due to processes that are during the birth of these black holes, during the collapse process. The magnetic field can transfer angular momentum out, and therefore maybe it is natural to form black holes from collapse, which are slowly spinning. So these are the kind of more like the population kind of information. There were also tests of relativity that are performed on these waveforms. So let me first briefly review several very standard tests. And then in the second part of my talk, I will talk more about some different physical theories that can be tested. Okay. So here in the first kind of test is a consistency test. So what you do is you break your wave into two pieces. The early part in the upper left figure, you have early part of the wave and late part of the wave. And what you do is you actually you use theoretical templates to to see what are the parameters that corresponds to the early part of the wave, and then you predict a final mass and final spin for the remnant black hole, the product of the merger, from the early part. And then you take your theoretical model, and then we measure the final mass and final spin from the second part of the wave. And we look for a consistency between these two tests, these two measurements, and we see whether they're consistent. I think the motivation behind this was that, if during the merger process, there is missing energy or missing angular momentum due to some additional physics, you measure discrepancy between these two parts of the waveform. But we did not actually see inconsistency. So this is basically saying that within the statistical accuracy of our detectors, the early and the late part of the waveforms are consistent. Another test, is going into more the so-called post-Newtonian expansion of the gravitational waveforms. So basically, you first say that let's parameterize the, write down our waveform. Okay, I really should, let me point this way. So you write down your waveform as an amplitude and phase as functions of frequency. And then you say that, okay, from theoretical modeling, I know how the amplitude should depend on frequency and how the phase should depend on frequency from numerical relativity simulations, which directly solve the Einstein's equations. And then we nevertheless write down the waveform as an expansion in terms of f to the some integer over 3. Okay, so this power law expansion corresponds to a 1 over r expansion or a v over c expansion, in the perturbative regime. So therefore, we have these coefficients which are supposed to be from numerical simulations, from actual theoretical modeling. And then we also measure these coefficients from the binary waveforms. And we look for discrepancy of the phase, especially the phase evolution of the binary that follow particular power laws. Okay, and these are basically looking for, it's a parameterized test looking for generic discrepancies from theoretical predictions. And this is not, there was no discrepancy, no significant discrepancy. Okay, and then finally, there's another parameterized test, which is regarding the propagation of gravitational waves through the universe. So here we were assuming that the gravitational wave at the particular frequencies would gain a particular phase shift in a particular power law. Okay, this corresponds to a modified dispersion relation. And then these different power laws, for different values of the power law, we can constrain the coefficients in front of these modifications. And basically, we have also seen that here in the data, from the data, there is no systematic discrepancy of the dispersion of the waves within our statistical uncertainty. So basically, from these tests, we're saying that we have measured, not only measured 100, or roughly an order of 100 binary black hole waveforms. They really seem to agree with the predictions of relativity, both in the generation of the waves and in the propagation. Okay, so this is the current status. We will continue into the future with gradually increased sensitivity, but we will also upgrade our facilities, upgrade our instruments within the LIGO facility, and also in Europe and in the US, we're proposing to have more sensitive detectors, ground-based detectors. So these are basically going to propose to increase our sensitivity by factors of a few, 3 or 4, on the ground, and then up to a factor of 20 or 30 if we have new facilities. So I will mention a little bit more why we want to have these new capabilities. Okay. So not only on the ground, there's also proposed space-based gravitational wave detectors. So as I mentioned, on the ground, we're looking for gravitational waves that are, from the several tens of hertz up to kilohertz. But in space, we will be able to probe gravitational waves that are in the millihertz band. So these will really target very low frequency gravitational waves that will be emitted by supermassive black holes merging, or by smaller stellar mass black holes plunging into supermassive black holes. So these projects were conceived in the 1990s, or maybe even earlier, okay? And then the current plan by the European Space Agency is to launch the LISA project in around 2034. And the LISA project is, interferometer that circles the sun, and the arm length is 2.5 million kilometers. There's also, proposed by Chinese scientists, the Taiji and the Tianqin projects. These are, the Taiji project is very similar on the left. It's very similar to the LISA project. I think it's kind of taking LISA as a model and to model after that, It's led by by various institutes in the Chinese Academy. The planned sensitivity is very similar to LISA, but I think the idea is that, I think it's a very interesting opportunity for research, is that if there are 2 space-based gravitational wave detectors in space, what will be some of the new science you're able to perform, in presence of both detectors in space. And the other thing is the Tianqin project, and it's a little bit different. It's proposed by Professor Luo Jun from the Sun Yat-sen University, also from Huazhong University of Science and Technology. Here, it's more like a Earth geocentric orbit. And here, the Tianqin project may have a slightly higher band of sensitivity than LISA and Taiji. So these are the space-based detectors. Not only will allow us to look for supermassive black holes, it also actually allows us to observe some of the white dwarf binaries. And actually observing white dwarf binaries may have consequences for understanding type 1a supernova potentially. So therefore, in the future, not only will we have improved sensitivities on the ground, we will have space-based detectors in the middle. And also, as I haven't mentioned before, there's a so-called pulsar timing approach for detecting gravitational waves that would even go lower frequencies. And these approaches measuring arrival times of pulses from pulsars. And these may be affected by gravitational wave that pass by, and therefore by monitoring very stable pulsars, this is a way to observe very low frequency gravitational waves. So one thing I want to mention is, if you think about the kind of black holes, these detectors, let's just talk about the ground-based and the space-based laser interferometers. They will be probing black holes with different masses. Also, I think the important thing is to see that they can actually probe to a very large distance into the universe. So in this diagram, so this shows that, okay, the LISA project is able to probe very heavy black holes, including the 10 to the 6 solar mass black holes, which are comparable in mass to as the Milky Way black holes. And these ones are believed to be at the centers of galaxies. And then if you look at the redshift they're reaching, well, basically they're reaching such high redshifts where maybe the first galaxies have not formed, or maybe, therefore the idea would be that they would really probe all the binaries that are merging, whose retarded time is within our observation time. Okay, so therefore it's very dramatic. And if you look at the Cosmic Explorer and the Einstein telescope in this plots, you will see that they also, for the 100 solar mass or 1,000 solar mass kind of black holes, or tens of solar mass black holes, they would also reach regimes which are kind of like the distance where we really think the first galaxies have formed. So in some sense, we can say that the reason why we want to build these capabilities on the ground and in space is that we will really want to reach all the binary black hole mergers that happen in the universe. Okay, so maybe by the 2030, 35 or something, when all the detectors, maybe it'll be 2040. Maybe by the time we build these detectors, we will see something different as well. Maybe we'll find out, oh, there's actually a lot more black holes at high redshift, which may lead to even higher redshift sources. That we don't know. But right now, I think we're really planning to be able to see all the binaries that would merge in the universe. I think this is really a very strong statement. And therefore, not only will we be able to probe the formation history, the population, but also very importantly, we can correlate the locations of these binaries that we have seen, including how far they are and where they are, and correlate them with the other indicators of large-scale structures of the universe. And this way, we will also have not only a tool for studying the evolution of the universe, but also the growth of structure or of the universe. Okay, so this is talking about the improved sensitivity. But let me then come back to testing relativity and testing black hole physics. So what are some of the things that we think we are going to be able to do theoretically with probing black holes, probing relativity? So one thing is, there are modified theories of gravity, for example, adding terms into the action, into the Einstein-Hilbert action, which are motivated by theories of quantum gravity. Certainly these are, maybe you might debate on, what is the scale at which they would appear. It's not clear, but on the other hand, these are basically terms you can add into the action anyway, and then you can predict what their consequences are, and you search for systematically search for deviations from the Einstein-Hilbert action. So one example is the so-called Chern-Simons gravity, which I have listed here. So it turns out it's a very interesting technical problem for people who are interested in learning about relativity, because it turns out, if you add this higher derivative term, these higher quadratic terms in Riemann tensor, you actually get higher derivative terms in your equations of motion. And then you may not have well-posed initial value problems. So I think from the EFT point of view, you may say, yeah, these are perturbative terms, which maybe are not supposed to become the dominant contributions in your calculation, and therefore they should be treated perturbatively. On the other hand, if you have a merging binary black hole, you don't want to be completely doing perturbation theory, because even in general relativity, you have nonlinearities within the R term. So I think one very exciting development in the past few years was by these approach where you first numerically solve Einstein's equations for binary black holes, and you use your numerical simulation as a background, and then you evolve the theta scalar field, and you evolve metric perturbations according to a new set of perturbative laws that uses the Chern-Simons parameter as a small parameter. Okay, so in this way, you basically evolve perturbations on top of a non-linearly obtained full numerical spacetime, and then you can obtain the corrections to the GR waveforms when the Chern-Simons correction is weak. So this is about thinking about a theory which are modifications of GR. So there are interesting features within relativity which are also interesting. For example, the so-called gravitational memory effect. So from the GR point of view, the idea is that if you have a free masses, and then if you have gravitational wave pass through the free masses, you'll find out that after the wave will pass through them, maybe the free masses, they will have a new configuration which is different from the old configuration, like this one, okay? So this had various ways of thinking about it, various levels of rigor and sophistication. So you can read it, Christodoulou in the 1990s connected this effect to a very general nonlinear feature of the general relativity. And then later on, these kind of memory effects was connected to the soft graviton theorem, and then also related to the information content of gravitational field. So therefore, this memory effect is has a very interesting theoretical kind of origin. So in gravitational waves, how does the memory effect show up? It'll basically mean that if you look at this train of gravitational waves, if you look very carefully at the end of the wave, it goes up like this. Basically, the strain, gravitational wave strain, would have some kind of non-oscillatory component, which will actually gradually increase and stay at a constant. Of course, the LIGO detectors won't be held at the constant displacement because these pendulums have restoring forces. But what you're supposed to see is that this ramp up actually will be detectable by the detectors. And it turns out that our sensitivity right now is not enough to detect a single memory effect from a single event. But if we stack together multiple events, it is possible to look for such a shift in the strain before and after the merger part of the wave. So this is about testing, this is about demonstrating an interesting feature in relativity. Let me give you another example about studying the horizon of the black holes. Okay, this is a little bit connectable to the previous talk. I think the immediate thing you want to ask is, now we have the so-called ring down part. Is it an oscillation of the black hole, or in what sense is it an oscillation of the black hole? As it turns out, depending on your definition of what a black hole is, it's usually not an oscillation of the black hole, because the ring down part of the gravitational wave is due to gravitational wave packets which are circulating the final black hole on the circular orbits, which are precessing and circling the final black hole. This is connectable to a WKB treatment of wave equations in a background curved spacetime. So basically, the idea is that if you see the quasi-normal mode ringing of the black hole, the ring down of the black hole, you have not detected the horizon, but you have detected the photosphere around the black hole, where null rays are circling the black hole on circular orbits. So then what about the horizon? We want to see the horizon, okay? So the horizon on its own, I think by definition from Stephen Hawking, would be that the event horizon is a location which separates the region where you're able to reach the black hole, where you're able to reach infinity, and the region you cannot. So therefore, if you think about it, the horizon, by definition, is something that you cannot see. But of course, if you have any structure which are a little bit outside the horizon, maybe then they can reflect waves and make the black hole not black. And I think that would be one way you can say, or at least my point of view of looking for these so-called echoes. Okay, so these echoes triggered a lot of interest in the past few years, and these authors claimed, probably wrongly, that they have seen these echoes after the main gravitational waves from LIGO events. So, and their explanation is that actually, if you have some signal, some gravitational wave that propagates around toward the final horizon, if you have some barrier, if the black hole is not a true black hole, but have some kind of surface corrections near the horizon, maybe these waves can be reflected from that barrier. But then these waves that are reflected, they actually get turned back by the photosphere of the black hole, and some of them will pass through the photosphere. So one way to think about it is to say that, yeah, the gravitational wave packet that gets reflected from the barrier, they try to escape the black hole, but a lot of them cannot escape because they're not propagating along directly the radial direction. So they get turned back and they go back to the barrier again, and maybe they can get reflected again and again. So therefore, you know, if you generically speaking, if you have some structures right outside the horizon, what you would expect is that if you send in gravitational waves toward the black hole, the waves may travel back and forth between this barrier, which are outside the horizon, and the photosphere, and then cause these echoes. So one way to think about is to see this space-time diagram, where I have this red line is a particle that falls down the black hole, and then together with the particle, it carries a gravitational wave packet. And then, you know, if you actually take the packet, the particle triggers a packet right outside the black hole on the photosphere. You know, it triggers a packet of gravitational waves that circles the photosphere, and that will give you the ring down wave. But some of these waves that propagate towards the horizon, and they may get reflected by the barrier and then come out as an echo, or they may be reflected again and give you another echo. And therefore, you know, this is a more detailed way to explain how the gravitational wave in the ring down is generated and how the echoes might actually form. So why are we so intrigued by the echo? I think one reason is just like it's not numerology, but it's a little bit like that. So if you think about the location at which the waves might be reflected from the horizon, and then you can say, oh, what about you know, a proper distance delta away from the horizon? What you find out is that if you reflect a wave from a proper distance delta from the horizon, it'll lead to the echoes, which are separated by 2 over kappa times a log of delta over the m. Okay, so the kappa is the surface gravity of the black hole, which is of the order of the mass. Okay, so or 1 over, yeah, maybe 1 over the mass. Maybe I got the wrong. No, it's 1 over the mass. 1 over the mass. Okay, therefore at the end, this thing is the mass of the black hole times the log of the proper distance of the reflecting location divided by the mass of the black hole. So what does it mean? It means the log is very intriguing, right? So this log is very important in various aspects of black hole physics, right? You know, if you ask Hawking radiation and unruly effects, it's all relatable by the fact that, you know, when you go close to the horizon, you have this logarithmic behavior. So therefore, it means that even if I want to have a Planck distance away from the horizon, the time difference between echoes is only 14 milliseconds. Okay, and the longer than 14 milliseconds means your distance is less than the Planck distance. So therefore, this really means that if you believe in echoes, you know, it means that you're able to probe structures which are really Planck scale above the horizon, whatever that means. Okay, Planck scale above the horizon. So this is the intriguing side, which is the good intriguing side. But of course, immediately you find out that if you believe in the classical physics of general relativity and the classical black hole physics, such reflection of energy from a distance, Planck distance away from the black hole is just such not going to be possible. Okay, so the one way to think about it is to say, okay, I have these gravitational waves, which are propagating into the extreme compact object. Okay, suppose this is a so-called tortoise coordinate system. So basically, the idea is that when your echoes are being reprocessed and then launched back to infinity, what happens is all of the energy content of your echoes are going to be squeezed within a region which is Planck distance away from the black hole. But the problem, of course, is that if you believe in the hoop conjecture or anything about black holes, if you stuff this much energy into a region this small, the whole thing will just collapse. And it collapses not because the energy hits the black hole and makes it collapse. It collapses because the energy content of the wave gravitates and prevents anything from escaping, okay? So it means that you cannot literally understand the echo from extreme compact objects as if literally there's a compact object which reflects waves. What really happens is that, you know, there's some mysterious non-local physics which are outside the horizon, which will make gravitational waves get reflected. So therefore, it shows that we can use this to test for black hole physics, but keeping in mind that it's very dramatic modifications of physics near the horizon that will give rise to these effects. Okay, so let me finally say that the other very interesting aspect of gravitational wave detection is also in the search of dark matter in this very specific way, where we know that for Kerr black holes, any massive scalar field or massive fields outside the Kerr black hole actually is unstable, in the sense that if you have the Compton wavelength of the particle comparable to a Kerr black hole, you will have the Penrose process, you know, it's the Nobel Prize winner. So as a Penrose process, basically it means that the energy of the rotation of the black hole is extracted, and in this case, in the form of a heightened amplitude of the scalar field. And basically, you know, if you have massive scalar fields like the axion, therefore they can be generated from these Kerr black holes, which are right, you know, after the merger of two black holes. And then there are proposals to search for these gravitational waves, and there are ongoing searches for such gravitational wave signatures from LIGO data. So let me just, okay, since the time is getting to the very close to the end, let me just very briefly jump into the other topic, which I also want to mention just for a little bit, which is that the detectors allow us to study relativity, but it also allows us to study quantum mechanics. Because the sensitivity of these devices are actually so good that they are really near, in some sense, near the limit posed to us by the Heisenberg uncertainty principle when you apply that to 40 kilogram test masses. Basically, so here it's a kind of like a so-called concept called the standard quantum limit. So the concept comes from the fact that if you measure the mass of a mirror, you will perturb its momentum because of the Heisenberg uncertainty principle. And then when you perturb the momentum, it'll cause an additional motion, and that motion would cause noise in your future measurements. So this kind of argument has led to the so-called standard quantum limit, which for LIGO poses a certain limitation of sensitivity. And this limitation is actually not far beyond our current sensitivity. This, as it turns out, this kind of limit can be surpassed by establishing quantum correlations between light and masses. So the theory of this has been proposed in the past 20 years, I guess, but it's only more recently that experimentalists in LIGO have achieved such a situation. Okay, so here I'm going to briefly show this noise curve. So basically here, these two, I think this curve shows the actual total noise that currently LIGO measures, and the quantum mechanical contribution from just quantum fluctuations would be this blue curve. And then when squeezed vacuum is injected in the appropriate way, the noise, the total noise is lowered in this region, just a tiny little bit in this region. But if you extract the quantum contribution of that, it actually corresponds to this curve. And this curve actually is quite below the blue curve. And it's also below the so-called standard quantum limit. So what it means is that even though our classical thermal fluctuations and other noise is still kind of high by a factor of a few, two maybe, it does demonstrate that if you inject quantum correlations into the detector, the masses are able to respond in such a way that the quantum noise of the detector is below this naive standard quantum limit set forth by using the Heisenberg uncertainty principle. So it does mean that the delta x times delta p of the test mass is not far below, not far above the h bar over 2. So it means that these microscopic masses are actually moving in the quantum regime. So people have thought about ways of doing this, ways of using this fact that whether you can, what can you do? Certainly you can think about ways to say that we can prepare quantum mechanical states for these macroscopic objects which have no classical counterparts. And then, there were a lot of recent interests in answering the question, or maybe addressing the question of, using considering using using gravity to transfer quantum entanglement, and therefore explore the interface between quantum mechanics and gravity in precision measurements experiments. I think this is maybe LIGO is not the best way to do it, but the related technology in so-called optomechanical systems, it will be one interesting way to probe these questions experimentally. So let me end my talk by showing the summary slide again. I think using the gravitational wave data, we not only measure the populations, not only speculating, but actually explaining the origins of these binaries, how they have formed. And then we will move on to more demonstrations and tests of non-trivial effects in relativity, and putting bound on alternative theories. If we don't see the echoes, and then we will bound how black the black holes can be, and also, correlating with large-scale structures, trying to understand large-scale structures of the universe. And finally, the quantum technology in LIGO is at the frontier of understanding macroscopic quantum mechanics. Thank you.
Any questions?
I saw one question on the Q&A. Should I answer the question on the angle between LISA detector orbital plane and the detector plane and the orbital plane is 60 degrees? Is there a reason for that? I can answer this question. I think this is understood as a very stable orbit because, as it turns out, if you put three things, the three things are actually each following a heliocentric orbit in such a way tilted so that it appears that they have this triangular formation around the sun. So if you only have the sun, if there's no Earth and no other planets, this triangular orbit configuration, which is tilted 60 degrees away from the plane of the orbit, is the stable configuration. And if you use any other angles, it won't be stable. I think that's the reason. But of course, now we have perturbations from the Earth and from other things. Then there are more detailed calculations of the orbit that will make sure that the orbit does not deform too much during the mission time.
Any more questions?
So, LIGO have any, you mentioned the squeeze talking down below the scalar probability. LIGO any friend in O4 do that?
Sorry, I can't hear the question very clearly. Either use the microphone or the.
Yeah, sorry. I just wondering when did the brain of the LIGO going to adopt this squeeze bucking to reduce noise to the beyond the standard probability?
Oh, sorry, I still can't hear. It's about the squeeze vacuum, right?
Yes, and I was wondering when did the LIGO plan to adopt this scheme and make it work?
Oh, I think right now the LIGO's plan is to upgrade to A+, which is using the so-called filter cavity. Okay, so this is I think right now the squeezing can already improve LIGO sensitivity, but there's a there's a planned A+ upgrade, which will install a so-called a filter cavity here in between the squeezer and the interferometer, so that when you use the squeezing, the phase squeezing here would improve the sensitivity without having the anti-squeezing of the amplitude here jeopardize your low frequency sensitivity. I think, I don't know exactly the plan of the A+ upgrade, but I think it will certainly be done. And that will be before, this will be before the so-called Voyager upgrade, which is a more ambitious one with cryogenic systems and higher laser power. So A+ has already been planned and will happen. I think right now, I don't exactly know the schedule though.
Right.
Can you hear me?
Yes.
So thanks for the nice talk. Is it convenient for me to get you to get to the slide where you showed the action for dynamical Chern-Simons theory?
Oh, the Chern-Simons. Yeah. Okay. Yes.
Hey, thanks. So the chair of this conference isn't here today, but I just want to briefly comment that some time ago, together with other collaborators, he found a solution where the background isn't just GR, so he turned on a free scalar field for data, which can be interpreted as the axiom. And they studied gravitational perturbations about this background. And they found gravitational wave solutions, which are interesting in the sense that the left circularly polarized wave and the right polarized waves travel with different dispersion relations. So that's the well-known birefringence effect. So I was just curious whether, in this case, you mentioned that you use GR solution as the background, and supposedly you turn off the theta field. Do you get something that is similar?
Yes, I think so. So you will have a birefringence there. I think the most interesting birefringence effect is in the, or easy to explain one, is the so-called ring down process. So in the ring down of black holes, usually there's a feature called the isospectrality. Okay, isospectrality means that the electric type quasi-normal mode and the magnetic type quasi-normal mode have the same set of eigenfrequencies. So this is very unusual for a microwave system or for any other resonant systems. Because, for example, in microwave cavities, the TE and TM modes have very different spectra, usually. And the magnetic dipole, electric dipole, magnetic dipole, quadrupole, all the radiations are not supposed to, generically speaking, have the same eigenfrequency. But for black holes in general relativity, they have the magnetic type and electric type ring downs originally have the same set of eigenfrequencies. But in the Chern-Simons case, there's a break of that isospectrality. So basically the ring down spectrum is different for electric type and magnetic type ring downs. And they are basically different polarization states of the ring down wave. So therefore, this is like a birefringence for gravitational waves propagating near a black hole. I think this is one example. Another example, I think, is in the Chern-Simons theory. When you apply the Chern-Simons theory to the universe, I think actually just the propagation of the gravitational wave actually has a natural birefringence. When you consider an expanding universe, and then I think actually different polarizations of the wave are already propagating at different speeds. So therefore, there is a birefringence as well. But personally here, in the more relevant to the slide here is this ring down process have a split spectrum. I think that corresponds to the birefringence here in the strong field regime.
Thanks.
Here I have a question. On theory side, there are quite a number of studies of symmetry breaking, like yet-to-weak phase transition or CC breaking, and they make some prediction for the gravitational wave detection. But in about how many years you expect you may be able to see some of this kind of gravitational wave generation?
I think my naive understanding is that the LIGO's observation spectrum is a relatively narrow one in comparison with the possible phase space of all the possible phase transition scenarios. So therefore, I think this is always a target to look for phase transition stochastic backgrounds, both in LIGO and in LISA, but it's not really clear when we are detecting these stochastic backgrounds. So another effort, which I think I didn't mention here, which is that I think another band of interest is the frequency band in between the LIGO and LISA band. And in here, I think there were conceptual designs of detectors like the SIGO detector made by Japanese colleagues, and also the Big Bang Observer detector proposed by people in the US, where they target this band where, relatively speaking, astrophysical backgrounds are more easy to remove, and they might target the stochastic background from inflation. But that depends on the model of inflation and how strong the spectrum can be. But there's a very ambitious plan of searching for that background as well. So yeah, so I personally don't know how long it'll take though. It'll be very exciting to find that.
Thank you. So, there's more questions. See that you don't see more questions. We thank you, Professor Chen, for this very exciting frontier.
Yeah. Probably need to turn off the notes.
So we are very lucky to have an on-site meeting. So I consider that it's a fortune for both the audience and the speaker. So our first lucky speaker is Vogel from Institute of Physics Sinica. We will talk about searching the light particle with supernova and the quantum ray.
So thanks for a nice introduction, and it's again a great pleasure to be able to be here to talk about some of our research outcomes over the last year, mostly. And yeah, so to not waste time, let's just go ahead. So this is the introduction, and the next page will be the outline. So the bottom line of this talk is trying to see basically what this sentence says. How can we help hunt down for fragmentation particles with actual physical objects or actual physical phenomena? Okay, so on the left-hand side, what you see are like all different kinds of possible theoretical candidates for explaining dark matter as a particle. And on the right-hand side, those two plots shows you the observational evidences coming from cosmology and then from actual physical observations that indicates the existence of dark matters. Yeah, so but the linking between those are still missing, as everybody knows. So there are tremendous effort in all different disciplines trying to answer or to tackle this difficult question. So what we are working on over last year was a small part of it, trying to see how much we can learn, or how much we can help with actual physical stuff. All right, so this is a real outline of the talk. So I will firstly spend some time to talk about how can we possibly constrain the unstandard models particles with core collapse supernova that will be further introduced in great detail by Guo Chen in the next talk. And I will try to see if I can go over all three different topics that I want to speak about. The first one is the KEV sterile neutrino, and the next one is the dark photon photo dark sector. And the third one is the work mostly done by Tsing here about EV sterile neutrinos. And then let's see, if time permits, then I would see how much I can talk about the potential way of improving the constraint on some GeV dark matter nuclear interaction using the scattering with cosmic rays. All right, so the first thing, yeah, constraining particle beyond standard model, which is called supernovae. Okay, so although unfortunately we'll talk about in great detail, I think I should still spend 1 minute to just give a brief overview of what collapse supernova is for everybody sitting here and online. Yeah, so the phenomenon of collapse supernovas you can see in this picture on the right-hand side. This guy is a supernova. Yeah, so it produces a tremendous amount of light, but can overshine almost like an entire small galaxy, for example. And then this kind of very explosive and energetic events signify the death of massive stars for mass of roughly bigger than solar mass at birth. And we know that there are the most likely ways to produce the non-neutron stars and maybe some of the black holes. Okay? And we say that it's very bright. And in terms of the luminosity in the electromagnetic emission, the energy luminosity is something like 10 times of the solar luminosity and lasts for roughly an orders of 100 days or so. So the corresponding photon energy carried by such an event or produced by such an event, you can calculate it easily, would be something like 10 to the 49 ergs. Okay. And this is just a minority of the total energy budget involved in this kind of event. Because like if you make if you do a fitting the photon light curve, then you immediately figure out that the explosion energy carried by the expanding ejecta is almost like 2 orders of magnitude higher than the energy you collect from the photon emission, which is 10 to the 51 ergs. Okay, and the traditional unit in our community called 1 Davy. Okay, and that is still only 1% of the total energy being emitted. And the over 99% of energies actually being carried away, produced in such a collapse event, is carried away by neutrinos. And so collapse supernova, you can consider it as like the universe, the nature's strongest neutrino emitter. Okay. And in terms of the occurrence frequency, roughly every second, there's one collapse supernova going to happen in the whole universe, in the visible universe. And the rate in our local Milky Way was estimated to be roughly like 0.5 to 2 per century. Okay. All right, so what is the physical mechanism driving supernovae? It can be basically summarized in one plot like this. Yeah, so initially you have a progenitor star with a central iron core that is becoming like a degenerate electron relativistic electrons. And the iron core size is about a few thousand kilometers, and the core density and temperature are indicated here. And the mass, you know that for such a system supported by electron degeneracy pressure, there's a maximum energy that can be maximum mass that can be supported, namely the Chandrasekhar mass, okay, which is about 1.4 solar mass. Okay, so once there could be further accretion, or there could be other mechanisms that somehow kind of decrease the electron degeneracy pressure, then the whole core will become gravitationally unstable and then collapse until further forces stop it. And then that is this process drawn by this, sorry, difficult to use, by this line. Yeah. So it will go through the collapse and then become a proto-neutron star. Okay, and then you can immediately see that the final stage of the proto-neutron star is something with a radius of about 10 to 50 kilometers. Okay, yeah, and so you can estimate how much gravitational energy should have been converted into other types of energy, and that gives you something like 10 to 53 ergs showing the middle of the plot. And then all those energies will eventually be mostly carried away by roughly 10 to 58 numbers of neutrinos in the time scale of 10 seconds. Okay, and those neutrinos are produced by all those different processes shown in the bottom left of the slide. All right, so these are not just the theory, yeah. So the supernova neutrinos that has actually been were once detected more than 30 years ago in the event of 1987A. And at that time, our neutrino detectors are not as big as what we have now. So at that point, even if the supernova happens relatively close, at roughly 50 kiloparsec away from the Earth, we only managed to detect around 20 events. of electron-active neutrino flavor. Okay. However, based on those 20 events, the reconstructed or the fitted neutrino luminosity and the average energies given there are consistent with broadly consistent with the supernova theory prediction. Okay. And if there's a supernova that happens today or over the next decade, then we expect that we will be able to see in our galaxy. Then we expect that we will be able to see roughly more than a few thousands up to say 10,000 neutrino events in all different detectors and in all flavors. So that would provide us much more information than what we had more than 30 years ago. All right, so the rest of the talk will be focused on PSM physics. Yeah. So why do we think that we can use the supernova-related observation to constrain in young standard model physics models? And that is because we mentioned that most in the traditional picture, assuming standard model only, then all the energies are basically carried away by neutrinos. That is because neutrinos is the most weakly interacting particle in standard model. Okay. However, if you imagine that there are beyond standard model particles that interact with baryons or non-leptons or photons, even weaker than neutrinos, then they can escape faster or easier relative to neutrinos. Okay, so that means that they might be able to, instead of neutrinos carrying away all the gravitational binding energies, those kind of weakly interacting particles, if they exist, they might be able to carry most of the gravitational binding energy, the energy source. Okay, so in that sense, so if your weakly interacting particle carries more energy than neutrinos, then you wouldn't be able to have so much energy being carried by neutrino, right? And then we have already learned that in the previous slide, we have already learned that we know what are roughly amount of energy carried by neutrinos, and then we know the emission time scale is roughly 10 seconds. So that tells us that you can use that to constrain the amount of energy carried away by any new particles. Okay, so this is a famous Raphael criteria given here, that the energy luminosity carried away by any new particles that may possibly be produced in the supernova explosion has to be smaller than roughly the neutrino luminosity, which is roughly 3 times 10 to the 50 ergs per second. Okay. And this has been was proposed at like shortly after 1987, and has been applied to many potential PSM particles since. All right, so then let's look at quite a few of them. So the first thing I want to talk about is KD sterile neutrinos, and they are like the hypothetically new neutrino species or new neutrino flavors that is beyond the known 3 kinds of active neutrinos. Yeah, and the motivation is that one motivation is if they exist and if they slightly match with active neutrinos, then they might be the warm dark matter candidates. Okay, so that was proposed early on. And there were also some observational anomalies or hints, or probably not calling evidence anyway, that some observations a few years ago in 2014 particularly, they see some X-ray excess in 3.5 keV lines from the center of some dwarf galaxies. And one interpretation was that it may be produced by the radiative decay of sterile neutrinos of mass of roughly 7 keV, okay, which is indicated in this yellow star shown here. All right, and there was a mixing angle of roughly psi squared 2 theta of 10 to the minus 10. Okay, so if those kind of sterile neutrinos with roughly speaking is keV mass and the mixing angle shown in this plot exist, then they can actually be produced quite efficiently inside a proto-neutron star. Okay, so the production can be done by 2 different mechanisms. The first one is through the so-called adiabatic flavor transformation through MSW-like resonance, exactly in the same way as solar neutrino going through the solar envelope, solar density envelope of the sun. And the second one is through the scattering production by the mixing, immediate mixing. Okay. So yeah, so those kind of production has been used together with Raphael's criteria by some people like Gravitational et al. In 2016 to place like say, okay, if such kind of neutrino should exist, then the supernova Raphael spark should be able to exclude the parameter range enclosed by this orange shaded region. All right. However, what we found out is that when people apply Raphael's bound to the cooling and use the super cooling constraint to constrain sterile neutrino, one important aspect was missing. Yeah. So the aspect that was missing is that they didn't include the feedback effect of sterile neutrino production and the physical properties of the proton star interior. Okay. So the idea is, I don't go into detail, but the idea is very simple. That to have a sterile neutrino production, they are basically produced asymmetrically in the sterile neutrino and the sterile anti-neutrino sector due to the existing asymmetry inside the proto-neutron star. Okay, so for example, you can see its right-hand side picture here. The axis is just tiny, forget about it for now, and the y-axis got two lines. One is for sterile anti-neutrino production. The lower one is for sterile neutrino production. And you can see that there's a strong asymmetry between. Okay, so if there's a strong asymmetry in the sterile neutrino and anti-neutrino production to begin with, then this asymmetry will create or further enhance the asymmetry that has already existed in the proto-neutron star in the active sector. Okay, and then you can imagine that if you increase further the asymmetry between active sector, then you are having less phase space to convert your active neutrino into sterile neutrino. Okay, so this is like a self-feedback mechanism that will suppress largely the sterile neutrino production, which is shown as the evolution of time in this plot, for example. Yeah, so you can consider like this delta T equals to 0 would be the sterile neutrino production rate without taking into account the effect of feedback. And when taking into account the effect of feedback, then you can see that particularly for sterile anti-neutrino production can be suppressed by roughly or close to a factor of 100. Okay, for a given particular parameter. And this just shows you the creation of the asymmetry in the new tau neutrino sector inside the supernova core. Yeah, so initially, the chemical potential of new tau should be 0 because tau is very heavy. You cannot produce it. You can only produce neutrino and anti-neutrino separately. But you have sterile neutrino can be converted from tau to S. Then it will create asymmetrically. Then it will create a net chemical potential for new tau. Over as time goes on. Yeah. So the similar mechanism also works if you consider the mixing between electron neutrinos and the sterile neutrinos. And so we deal with both in these two papers shown there. And then we basically show that the effect can be shown in a snapshot by these two plots. So the left-hand side, there are two lines, these blue lines, and then the brown lines are the constraint that we derive, assuming there's no feedback from Raphael's bound to sterile neutrino. Okay, so you can see they are kind of similar to what we saw before. And if you include the feedback effect, then you see that the constraint between the mixing of electron neutrino and the sterile neutrino completely disappear out of this picture. So that's why you don't see a blue line. While the case for the mixing between tau and the sterile neutrino also be largely shifted to much larger mixing angle. And so basically they cannot be competing with other X-ray bonds. Okay. So yeah, so when by including those effects, then we largely let the supernova constraint to the sterile neutrino basically. Okay. So then let's discuss the second object of this talk. The second thing I want to talk about is also a constraint, similar constraint that has been put on the dark sector photo by dark photon. Okay, so it was proposed also early on by some theorists that there might be the dark sector might exist with a dark photon, kind of like parallel set of standard model photon, but with a finite mass, and they can mix with tiny mixing with standard model photons. Okay, and if such kind of and then they can also have their own interaction with the potential dark fermion given by chi. So dark photon is location is A nu. And those dark photons, A prime, or the dark fermions, potentially independent of dark matter, chi and chi bar, they can also be produced inside the photoneutron star by a different number of processes. For example, by the nucleon branch pattern shown here. Also by the inverse competent, for example, of this process. Or they can also decay or be pair created by, say, electron-positron pair, for example. Okay, so there are a number of processes that can produce, and provided that the mass are below roughly a few hundred of mega electron volts. Okay, so similar Raphael constraint has also been used to place the mixing parameter or the parameter space of the spark sector. And then, for example, if you completely ignore the degree of freedom of dark fermions by considering only the dark photon, you can say, okay, the dark fermion is too heavy, and photon maybe the mass range of a few hundred mega electron volt, then I don't care about dark fermion in the supernova environment. Then there are many recent works, they try to look at this problem, and then they can typically put a constraint from the Raphael's cooling bound and the mixing angle epsilon and the dark photon mass here shown as m prime in this parameter space. And you can see that it complements with some other bounds, for example, like the late decay or from the stellar horizontal branch charge or from other terrestrial pin dump experiments. Okay, to fill in this part of the parameter space. Okay, and there are also other bounds that one can put additional to Raphael bound, which one is what we proposed last year. That's a bit bigger than that, and then the other one is from the gamma ray anyway. Okay, so supernova has been considered as a useful prop or useful prop to constrain the dark photon mixing with standard model photons. Okay. And more recently, there are a couple of works examine the potential constraint of sub-GeV light dark matter with supernova. Okay, and then again using the similar cooling constraint. And for example, the left-hand side picture shown from Chang et al. In 2018 shows that once again supernova can provide a good constraint on this parameter space, okay, below some experimental reaches. Okay, however, and the right-hand side is somewhat similar. Okay, and one thing that has been ignored is that here they typically assume a relatively big coupling factor in the dark sector, like for example alpha d equals to 0.5 here. However, when they derive plot, the self-interaction between dark matter or dark fermions or dark particles were completely ignored for some reason. Okay. So we try to also working with previous research assistant Alan in our group. We try to also revisit this issue and try to compute what is the self-trapping effect of dark fermions and with dark photons inside the environment, okay, for sub-GeV dark particles. Yeah, and those are preliminary plots. But what you can see here is that, so there are two lines. So let's just look at one of them. Maybe look at the left-hand side. Yeah, so the x-axis is the dark fermion mass, and then the y-axis is the alpha d phi structure constant in the dark sector. And here we assume that the dark photon mass is 3 times the of dark fermion, assuming a particular mixing angle of 10⁻⁸. And what this line shows you is that for any region above this line, there is no supernova constraint. Okay. That is simply because the alpha d's are, even if it's tiny, but if we just 10⁻⁻10, and even down to 10⁻⁵ of alpha d, the self-trapping effect of dark matter, dark sector, will be enough to prevent any of them from leaking out. So the Raphael constraint will not be able to be applied to dark sector, with a moderate self-interaction. Okay. Only those having very tiny alpha d, you can use supernova constraint. Okay. So yeah, this is we're still trying to wrap this up, and this same mechanism, I presume, it can also be applied to other stellar bounds, or they can be also be interesting for generating dark matter inside the neutron star. Okay, so the third thing that I want to talk about supernovae is how can we use it? So we previous two ones were like we erase some bounds. Okay, so we are good at erasing the bounds, and whether we can use supernova to do something good for concerning the DSM star. Yeah. All right. So one candidate that we thought of together with Tsing is that we think that okay, it's related to the issue of EV sterile neutrino. Okay. So if some of you may remember that almost like 8 years ago, there was reported anomalies from short baseline reactors shown in this plot, where in the baseline of say sub-kilometers, they see a slightly less neutrinos than expected from the anti-electron neutrino produced by reactors. And there were also earlier anomalies reported by RSND, and the recent one by Univ, sort of like inconclusive anyway. Yeah. And then all those anomalies might be reconciled if like EV or roughly matched range of EV sterile neutrino exists. Okay. And we also heard this morning that there's a Hubble tension, and then one proposal to solve that is that light EV sterile neutrino that are self-interacting strongly among each other, then that may also help to reconcile the Hubble tension. So there are some motivation for this kind of strange particles. Okay. So anyway, so unlike EV sterile neutrinos, the EV sterile neutrino they will not be produced from deep inside the proton-neutron star. Okay. So the production mechanism is more that your proton-neutron star emit the regular active neutrinos, and then when active neutrinos propagate on their way out through the stellar envelope, then those active neutrinos can be converted into EV sterile neutrino. Okay. So with supernova cooling bond, they don't do anything for EV sterile neutrino. Okay. However, so the question that we ask, first question we ask is, we have supernova neutrino data from 1987A. Can we use that to constrain the EV sterile neutrino? I say if they are produced, then some of them may be converted on the way out. So we supposedly should see a reduction of the neutrino flux. So this is the question that we first ask. And it turns out it's difficult because at that time we only see one neutrino flavor, and then we have very few events. And we detect those neutrinos over the time scale of 10 seconds, for which we do not know the very well, even without any exotic physics. Yeah, even for active neutrino themselves, we cannot predict reliably their arrival flux. So the next question that we want to ask is, can we rule them out when the next galactic supernova occurs? Okay. So this part, I'm sorry that I have 4 panels here. Yeah, but basically what this part shows is the left-hand side the normal mass neutrino ordering, right-hand side is for the inverted neutrino mass ordering, and then the top ones are the flavor conversion probability, the flavor survival probability for an electron neutrino remaining as an electron neutrino, and the lower ones are the flavor conversion probability of an electron neutrino going to a mu or tau neutrino flavor. Okay, and from what you can see here, that and then the x and the y-axis are the mixing parameter of these EV sterile neutrinos. So from what you see here is that independent of which mass ordering, you will see that over a wide parameter space, you don't see this conversion probability is like 0. Okay, so that means that whatever your electron neutrino are having initially, they will be always converted to sterile neutrinos. Okay, so that's a bottom line of this plot. So they will be carried as a sterile neutrino. Okay, so then Tsing go ahead and calculated all those predicted event or expected event for galactic supernovae at 10 kiloparsec for different type of detectors, including DIN, Hyper-K, and the Juno. Okay, and then we only focus on the very short time window, the first 10 milliseconds of a supernova event. That is because that is the only phase which we understand the oscillation physics better. Okay, so within that of the 10 millisecond, we can still, the neutrino detector we expect them to still detect a sizable number of events. Yeah, and for the case of standard non-sterile neutrino mixing, then those total event numbers are given by here, the very top line. Okay, and then if you use some different mixing parameter sets, then you can see that for the case of normal ordering on the DIN, the events in the DIN is roughly comparable, only slightly reduced. Well, the events in the Tiger K can be reduced by roughly a factor of 3-ish. Okay, similarly for Juno. Okay, so with this reduction of detected event, then the gene can go ahead and then construct the chi-square and then draw the exclusion limit. And then this is shown on the left-hand side, for example. Yeah, so the red line is work. And so everything on the right-hand side, if there's a next galactic supernova that happens, then all these parameter space can be excluded by the supernova neutrino detection. And the right-hand side just shows you the sensitivity. And the bottom line is that for any heavy stable supernovae that happens within our Milky Way, up to a few tens of kiloparsec, you will be able to confidently draw out a sterile neutrino sitting in this parameter range. So how much time do I have? 5 minutes? Okay. All right, so I have 5 minutes to go through the cosmic ray related stuff, which is largely motivated by Smith sitting here, and mostly done by the numerical work, and most of the work are done by Gang Guo, who was a postdoc in our institute and now is back in China. Okay, so the motivation was, again, back to dark matter, that we want to search for dark matter, and however, the dark matter searches for super GeV1s, heavier than GeV1s, is so far see no results, no signals. There may be one possibility, but yeah, we don't know yet. Anyway, so this partly motivated the consideration of all other candidates with different masses or interactions. All right. And it was proposed in 2018 by Breland et al. And Ama et al. That if you assume there's a scattering, there is an interaction cross-section between dark matter and nuclear, then the existence of cosmic ray that propagates in the interstellar medium or in the Milky Way halo or in the intergalactic space, the same interaction will be able to accelerate a bit of dark matter sitting there. Okay. So similarly, just like so in the sense that we know in the standard model particle sector, we have those non-thermal spectra that are like a power law. And then if there are any potential interaction between standard model particle that have this power law, that interact with dark matter particle, which are sort of visualized in anywhere, then they could generate also a subcomponent having a power law in dark matter, okay, not thermal dark matter component. All right, so then so that was done by those two works. And what's new in our work is that those works, they consider mainly the dark matter being generated or being upscated to an energy range of roughly a few, around GeV each. Okay, so where you can use the existing like neutrino detector or the low energy experiment to set constraint on those upscated dark matter component. However, what Gang thought of was that, hey, we have the ice cube detector that is capable to detect the particles having, say, roughly PeV-ish of energy. So we know cosmic ray has energy extending out to EV. So how about we have a look at how much dark matter can be upscated to the energy range that ice cube can probe. Okay. So what he does is then basically follow what Simulate done before. We just assume that there's a cosmic ray uniformly distributed in our Milky Way by a flat size of disk. And then we assume we take a few different dark matter profiles, and we assume a given dark matter nuclear interaction cross-section, and then we can just use the simple formula to calculate how much dark matter can be accelerated. Okay, so this part shows you the results, like those red line and the black line are the upscated dark matter flux in this energy range. For two different dark matter masses. The upper one is for 1 keV, the lower one is for 1 MV. And in comparison, also shown like the astrophysical neutrino being detected by ice cube, fitted by a power law, shown by this orange line, okay? And the cosmic ray, primary cosmic ray spectrum, multiplied by 10 to the minus 2. Okay, so you can see that for a cross section that is roughly like 10 to the 30 at this energy range, centimeter squared, the upscaler dark matter component of flux can be comparable to that of astrophysical neutrinos. So this immediately tells you that ice cube will be able to probe the dark matter cross section at this energy range that is roughly comparable to the neutrino proton cross section. Okay, because their flux are comparable. All right. So then, using those similar methods, and then just scan over different dark matter parameter space, then you can also draw a good distribution plot as shown in here. So yeah, so forget about the extragalactic component. So for let's just get the galactic component here. Then you can see that this constraint that derived by considering scattered high energy dark matter component ice cube can confidently robustly exclude the sub-GeV dark matter with cross-section roughly ranging in between 10 to the minus 32 to 10 to the minus 28-ish. Okay, and the neutrino proton scattering cross-section in this energy range is sitting roughly somewhere here, a few times 10 to the minus 34. So as expected, yeah, this constraint can be put close to the neutrino proton scattering direction. And one question that we are often being asked is how does this constraint being compared with low energy sphere? Because this cross-section is determined at high energy scale. So to do that, you need to do extrapolation, or you need to have a good model. Okay. So if we do a very simple naive extrapolation, assuming that cross-section just goes proportional to e to the alpha, where alpha is a power law, then you can basically just shift the direct constraint to somewhere down there. However, we more recently realized that this is just a very naive. So what we do is that we consider a particular model, Gang consider a particular model, where you just consider the interaction between dark matter particles with standard model quarks of barons with exchange of a vector particle. Okay, and with that, then we also consider the potential generation of the inelastic signal, because you can imagine if a cosmic ray coming in with such an energy collided with a dark matter particle, it can easily exceed the threshold production for delta resonance. So then you can produce also high energy photon and the high energy secondary neutrinos. So all those are, I don't have to go into detail anyway, I can look at a paper here. So those are the predicted high energy gamma ray and the neutrino flux shown there. And unfortunately, when we consider such a kind of model, which is primarily the differential cross-section is located in a low Q square, then our new proposed constraint cannot compete mostly with the low energy experiment like Xenon one time, for example. Yeah, that is simply because of the differential cross-section dependence. However, this is, so we look at this like an example that, well, if you have some kind of interaction type that is not so relatively enhanced in the low energy Q square, then this kind of constraint might be interesting, but we didn't go further to pursue that. So I think I run out of time, so I will just leave my summary page here, and then thank you for the attention.
Since Norman has used up all his time, so we maybe allow one or two urgent questions. Anyone? You just okay. So since the capability of testing this BSM particles depends on the amount of neutrino that we have observed. So does this capability largely depend on the distance of the supernova?
Okay, so there are a few questions, right? So the first one is, for example, for the case of EV star neutrino, that we really need to have a future supernova, and then the total event number will determine how good we can put a plot to get the constraint. So in that sense, it's depending on that for that particular case. Okay. And what we show is that, well, as far as up to say 2030 KPC, we can put similar bounds. And then for the case of Raphael constraint, that is independent of that the concern has been improved test now because we have the test event of magnetism.
Yes.
So in a sense, for Galactic, if you just simply apply Raffles constraint, then it is independent of any new coming supernova explosions. But if you say you want to further use that, if your next supernova happens, then of course that will depend on the distance.
When you talk about the stereo internal feedback, would this bring it back into the thermal equilibrium?
So if I understand correctly, yeah. So there can be sterilization being produced in a deeper layer, and then they may be so some electron or tau neutrino can be produced in a deeper layer, and then they may be transformed back to an active flavor in outer layer, and then that would in fact change the temperature of some supernova matter around that layer. Where you have so basically it's an energy transfer process from inside to outside that is forbidden by a certain amount of particle. And then one of the what we took that into account, and the temperature variation was roughly around factor of 2-ish.
Is there any question from the
Yeah.
Yeah, maybe you can answer
So
these questions.
the questions in the first question, can one do similar axis to Axion? I think so. Yeah. So like some people actually, quite a number of people actually do it, and so to repeat that work, then we need to find an even better motivation because some of was already done by even recently by Irici et al. The first one. Yeah. And well, if you have a model that has self-tapping in whatever sector you have, like Axion, then our new erasing the bound can be applied to that. I would say so. And then I have several reference value of can all this too. Oh, okay. Probably not. So only some of the listed values can be used to explain the baseline anomaly. What do we mean by generating that table is just to see over which range of the parameter space the ED sterile neutrino might be go up. Yeah, so we try to do it independently from the ED sterile shorter reactor baseline anomaly. I hope I answered your question, Ricky.
Okay, let's thank the second model for this nice talk. Our second lucky speaker is from local, Boqian Han from here. He will talk about 3D supernova simulation.